have it gives you problems, use the reading that I assigned in the book, or not in the book, on Canvas, on that PDF. There's some reading there. Go there. Do some research. All right. Cool. Insoluble solids form. Same thing. Go back up there. Do some reading. I'm counting on you to apply your sense of responsibility to do a lot of this. I'm not going to feed you the answers. So this is what when we're talking about insoluble salts, we're talking about double replacement. Double replacement. And with that, these two will going to switch. Literally, this one will kick that one out. So what we have forming would be a PbCl2. Now I get 2. This lead's a +2 because of this. Remember that? If these arrows crossing gives you confusion, come find me. PbCl2 plus NaNO3. Excellent. So to balance that off, 2 here and 2 there. Awesome. Guide to writing net ionic equations. Excellent. So, net ionic equations, and we touched on this before. Now, the net ionic equation is going to be, I'm going to skip down here, whatever forms the solid. That is what the net ionic equation is. The ionic equation includes all of the ions. All of the ions that are produced. So every compound gets broken up into separate parts. These are all separate parts. All separate parts. They break up. That's your ionic equation. Only the solid comes together. That's our net ionic equation. All right, here we go. Mixtures that form insoluble salts. Oh, so the first one was NaCl PbNO3. Starting with our original equation, as always. Hold on. Here's my ionic equation. Na plus Cl minus plus Bb plus 2 plus NO3 minus 1, and there's 2 of those. Cool. My net ionic. Well, at this point, I'm going to have Pb plus 2, and that's aqueous at this point, plus Cl minus, that's aqueous, yielding PbCl2, and this is going to be solid. If you're wondering why this is solid and not aqueous, go back to the reading, read the summary. If that confuses you, open the PDF, learn it that way. Here we go. So there we go. That's what we do. Separate all of our compounds into different ions. That's our net ionic equation. And then that's our ionic equation. Our net forms the solid. Excellent. Percent concentration, 12.4a is what I wanted to do. So percent, of course, grams solute, grams of solution, which includes the solute. I like these because it shows a quick example right here. Use the examples. They're really helpful. All right, mass percent, 18 grams of NaCl in a 90 gram solution. So we're just going to do 18 divided by 90 times 100%. Whatever that means, that's what we get. Cool. So this is my solute. This is my solvent, or solution. Sorry. Don't do this, don't do this, don't do this. 12.5. Okay, so we're looking at molarity. Molarity is important, probably the most important thing we're talking about. Moles per liter. Or, of course, the inverse, liters of solution per moles of solute. Very, 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 very important. When we dilute something, we're going to use this equation. M1V1 equals M2V2. Now, same as before when we talked about ideal gas laws, ones are for one state, twos are for another state. You can call it initial and final. You can call it 1 and 2, before and after, whatever you want, as long as you separate the different states. Okay, so let's calculate the molarity of the following solutions. I'm looking for moles of solute in liters of solution. So I have 145 moles of HCl. Cool, that's a solute in a 0.025 liters of HCl solution. Cool. So we have 1.45 moles divided by 0.25 liters. Whatever that is, that's what we're looking for. Let's see, get a quick calculator. Where did I put a calculator? Oh, tablet. How come I don't have a calculator? I'm just getting my old school one. Don't laugh. I'm still an old man. Still just use a small one. All right. I got 5. Ooh. Cool. I got 5.8 molar. Check my answer. Perfect. That is how you want to use it. Do the work, then check your answer. 5.8. Capital M is what we call molar. Cool. So put that up here. Capital M, molar. Moles per liter. Moles per liter. So in here you're given grams, convert grams to moles, divided by liters. Here you have grams, so you're going to convert grams of NaBr to moles of NaBr, and then you're going to convert milliliters to liters, and then divide them. So convert grams to moles, milliliters to liters, and then divide it. Excellent. We can use molarity the same way in stoichiometry. Just as a ratio, the same way we use molar ratio, same way we use density, same way we use ideal gas law, whatever it is, same exact thing. Nothing has changed so far. So, how many moles of HCl are in 1.5 liters of a 6.0 milliliter moles of solution? All right, so what are we going to start with? So this is kind of where it gets funky. Usually I say start with what's given, but here we're given two different things. Well, I asked for myself, what's the relationship between these two? And how does that help me find what I'm looking for? The relationship is I have liters times moles per liters. The liters were canceled, providing me moles, and that's what I'm looking for. So with that knowledge, I'm going to start with 0.15 liters, or 1.50 liters of HCl times 6.0, and I write it as I say it, moles per 1 liter. This helps me not get confused. You don't want to put 6 down here and 1 up there. If I go through and cancel my units, liters of HCl cancels, liters of HCl cancels, left with moles of HCl. Equals 1.5 times 6, looks like 9. 9 moles of HCl. Check my answer. 9 moles of HCl. Excellent.